Okay, hello everyone. Welcome to our presentation about our AI-driven dynamic pricing in retailing industry. So our objective was to use AI to forecast demand and to dynamically adapt prices in real time. So my team is composed of Timothy Burkutali.
So my name is Omar Schnemelen. I worked as the project manager.
And my name is Lucas Ognon, and I'm a data scientist.
And I am the business analyst. So we found a problem in a business problem. We find that the prices of products in retail stores are not always optimal, and stores are missing out potential revenues. So our main question is how to adapt and forecast the prices of a retail store to optimize its revenue.
So quickly, what's going to be our solution for that? So for the business scope, as we explained it earlier, it's going to be a dynamic pricing strategy based on the predicted demand in the retailing industry. And for that, we're going to be able to use the AI tool to forecast the demand in order to adapt the prices in a dynamic way to really maximize the profits and minimize the inventory loss. And what is going to bring to the stakeholders? So first of all, for the retail company, is going to increase the revenues and increase in competitiveness. And finally, for the stock manager, it's going to be a simplification of the stock management.
So why our product matters? So an optimization of the price using a reinforcement learning algorithm will allow the stores to increase their revenue, to predict more effectively the stock variations, and to reduce the risk of losses.
So for the methodology, how we work, so we start with demand forecasting because we need to anticipate the demand at all time in order to adjust the prices and the management of inventory. So we use reinforcement learning models, which are trained on the retail data sets to anticipate the trend of the demand. Also, we need to be estimating the elasticity of all the products at all times in order to calculate the effective price and to maximize the sales and to assess also the sensitivity to price modifications. And lastly, we did simulation and optimization. So we did the actual reinforcement learning models to simulate the sales volume variation and automatically adjust the prices in real time and to manage the stock in order to avoid any waste or any loss of stock during the process.
So quickly about the dataset we use. So we found it on Kaggle. The name of it is the retail inventory demand, and the size was 20 products on more than 3,500 stores. And we really use different features to train our model about the date, the store ID, the category, the region, the price, the inventory level, and the weather. These are all features that can really impact the demand of a price of a product.
So the metrics we will assess to evaluate the efficacy of our algorithm will be the sales revenue, because we can look how to maximize performance and growth. When we look at inventory level, we can optimize working capital and minimize the costs. And when we look at number of units sold, we can measure the demand and flow rate.
So now for the AI, we started with the simulation because we wanted to test the data set we had. So we did a model which we call the keep price policy. So the idea is to simulate, so this was on a 5-day period and only on one of the 20 products. So we wanted to simulate how much we did in the stores will do in terms of sales if we keep the price the same, and if we do nothing with the current inventory. So we did the first AI model, and it gave us results of a revenue of a bit less than $10,000, which we think is suboptimal, and we want to test this hypothesis later. And the objective of the future reinforcement learning model we will do is to test multiple price points to identify the elasticity zones where we will be able to maximize the profit.
So thank you.
No, it's maybe just for the exploratory data. I was thinking to explain it, to make it clear, we wanted to, at first, we were wondering, because on the dataset we had, it was split into 5 categories. And we were wondering whether we needed to calculate the price and the elasticity based on the category or based on each product. So what we did was an average of the price and the number of units sold based on the category to see if the category had an impact or not on the prices, the demand, and this kind of things. So what we noticed is, as you can see on the presentation, the average on each category is very similar, whether you are in electronics, groceries, stores, or clothing. The standard deviation being very low means that the category does not have any impact on the price and on the number of units sold. So this means that the dynamic pricing must be made not based on the category, but based on each product.
So thank you, Ruben. So let's have a look about the price versus the sales relationship. So this chart plots unit sold against price across our data sample. What we immediately see here is that there is not a strong correlation between the price and the sales volume. So for any given point, whether it's like $10 or $30 or even $80, sales can really range anywhere from 0 to nearly 300 units. So this wide dispersion tells us that traditional linear or economic model aren't sufficient to explain and or to predict demand the demand behavior here, because the relationship is so weak and non-linear that we need a dynamic pricing approach, such as reinforcement learning, for example, to allow the system to continuously test, learn, and adjust the prices in a trial and error environment, which is more compatible with this type of noisy and unpredictable data. So really here, the key takeaway is like we don't have a strong price and sales relationship, and static model are inadequate, and so we have to have an adaptive reinforcement learning based pricing, and it's very required. On this table, it shows the average product data across the 20 product sample, and what stands out is like how similar the average are from one product to another. So whether we look at the price, the unit sold, or the competitor pricing, and this consistency really highlights an important point, is that even though the average look almost identical, projects don't react the same way to price changes, and that's why using a single elasticity model wouldn't work here. And we have the need to use the individualized elasticity model for each project to accurately capture the specific demand behavior and make really better pricing decision. And about the elasticity analysis, so let's have an interpretation of that table. So first, most of the products shows a negative price elasticity. So this is expected. When the price increase, the demand decrease. However, 2 products display positive elasticity, and this can like really be from external influence or and requires like more data investigation. And second, we have like a really low R square. So this means that the linear relationship between price and demand is weak, and the price explains only a small part of the demand variation, meaning that the relationship is weak and non-linear. And so because of this, static linear models perform poorly, and a dynamic reinforcement learning model based approach is better suited.
So now what we did is creating a Q-learning algorithm. So the objective of this algorithm was to develop an AI agent that is able to achieve better performances than the fixed price policy that I explained to you earlier, which is what most stores do, since they don't change the prices of the product like every 5 days. So the Q-learning algorithm use reinforcement learning for this. You have all the rules of how it works on the right. So we only did it on one product for the example. The period we used is on 1 year. So we want to compare it to the baseline, which is the performance under the fixed price policy. So the baseline is keeping the same price that we have on the data set, and to reorder products when the inventory drops below 50 units in order to avoid the baseline failing, because the product will be out of stock in the simulation. And the policy of the reinforcement learning model is that it should optimize the prices and the reorder timing at all times, not only once a month or once a day. The goal is to maximize the total annual profits and to maintain a stock availability, but it goes a bit beyond that, because what it doesn't take into account is economies you make because you don't have any waste. If you remember, there was a grocery category. So for a grocery shop, for instance, you won't have to throw away any food if your algorithm can predict the demand accurately. So the overview is that the agent was trained through trial and error interactions. So it simulated an environment that suited the dataset with the 20 products and everything. So this one is only for product 1. But there was a reward function. So when the profit was improved and the stability was improved on the inventory, the algorithm will keep it that way, so it can improve itself. So it should adapt also, as Lucas said, not only to the price of the product itself and its relation to demand, but also to the seasonality of the product, whether there is a promotion, a holiday or not, so weather, all these type of things that can have an impact on the demand, and that the elasticity cannot take into account. So this is the result of the Q-learning algorithm. So as you can see, the baseline with the fixed price policy made a total annual profit of a bit more than $227,000. And with our trained dynamic agent, we made just a bit short of $340,000, which is an increase of 3.71% of capital, which is more than $13,000 on only 1 year, only one product out of the 20, which is only like 5% of the potential. So we can see that with just this agent, a retail store should be able to increase their sales revenue by this much. And again, it doesn't take into account the saving you make on inventory management. So, and the smarter stock turnover. Also, there is a foundation for a fully automated pricing and inventory optimization, so on all products, and maybe in other categories and retail in the future. So, thank you for listening to us, and if you have any questions, we are happy to hear them.
So again, thank you guys very much. Again, a round of applause.